In the vastness of the cosmos, an invisible hand binds all things. A quiet force, weaker than the flicker of static on a fingertip, yet stronger than the will of light itself. It is the pull that drops an apple from the branch, that keeps the moon in its endless waltz, that bends rivers of stars into spirals and galaxies into clusters. It is the gravity that cannot let go. To fall is to surrender, a raindrop sliding from the cloud, a comet arcing toward the sun, a star collapsing under its own weight. Falling is not motion alone, but the revelation of a law written into the bones of reality, a law that never rests, never loosens, never relents. Rivers drag ships toward their whirlpools, oceans pull tides to their shores, and space-time itself bends, curves, and folds beneath unseen weight. Gravity is the sculptor of worlds, the architect of orbits, the keeper of cosmic time, and yet, despite its familiarity, it remains the most mysterious. What is this force that both cradles and consumes? Newton measured its reach. Einstein bent it into geometry, but still its essence escapes comprehension. It is the weakest of nature's forces, yet it rules the heavens. It is the most universal. Of laws, yet the least understood. It binds galaxies across billions of light years, and in the heart of black holes, it forbids even light from breaking free. Gravity at once fragile and absolute, gentle and merciless, the oldest companion of matter, the shaper of eternity, the force that holds and refuses to let go. Long before equations etched the laws of motion, long before telescopes unveiled the silent ballet of planets, humankind felt gravity in their bones. They saw apples fall, stones tumble, raindrops slip from clouds. They saw the heavens swirl in circles, too perfect to belong to chance. And they asked, why do things fall? Why does the sky stay ordered? Why does the earth not scatter into the void? For the ancients, answers took the shape of myth. Aristotle, gazing into the patterns of the world, declared that objects fell because it was their nature to seek their rightful place. Stones yearned for the earth. Fire reached upward toward the heavens. The cosmos itself, in his philosophy, was arranged in perfect spheres, with Earth at the center, and every star and planet circling in crystalline perfection. Gravity, though unnamed, was explained as essence, an order imposed by nature itself. For nearly 2 millennia, this vision endured. The celestial spheres comforted human thought, predictable, divine, eternal. But then a quiet rebellion began. In the early 17th century, Galileo Galilei dared to test what others assumed. From the Leaning Tower of Pisa, legend says, he dropped spheres of different weights, not to prove arrogance, but to expose truth. The balls struck the ground together, not in order of their heaviness, but in the impartial rhythm of acceleration. Nature, he discovered, was not bound by philosophy, but by law. Motion, he found, was universal. The falling of a stone and the circling of a planet were not different categories of truth. They were threads of the same tapestry. Galileo's telescope turned upward and shattered the spheres of Aristotle. The moon was scarred, not perfect. Jupiter carried moons of its own, miniature worlds orbiting in defiance of Earth's supposed centrality. The heavens were not flawless or immutable. They were dynamic, restless, moved by a force unseen but everywhere. It was Isaac Newton who named that force in 1687. In his Philosophiae Naturalis Principia Mathematica, Newton unveiled the invisible tether that binds the apple to the earth to the sun, and the sun to the stars. Gravity, he declared, was universal. Every particle of matter pulls on every other with a force proportional to their masses and inversely to the square of their distance. The fall of an apple was not a parochial event, but the very same law that governed the orbit of the moon. For the first time, the heavens and the earth were united under one rule. The cosmos, once split between terrestrial and divine, was now one arena, one story, one law. The image of Newton beneath the apple tree is mythologized, but the truth is far deeper than legend. In the apple, he saw the moon. In the moon, he saw the planets, and in their paths, he saw an order that could be written in mathematics. Precise, eternal, universal. His law of gravitation allowed humankind to calculate the arc of comets, the tides of oceans, the shape of orbits. It made the universe predictable, measurable, knowable. Yet Newton himself confessed unease. He could calculate gravity's pull, but not its essence. That gravity should be innate, inherent, and essential to matter, he wrote, is to me so great an absurdity that I believe no man can ever fall into it. He had given gravity its formula, but not its cause. The mechanism remained hidden. Why masses attract each other across empty space was a mystery he himself could not touch. Gravity, in Newton's own admission, was an action at a distance, instantaneous, invisible, inexplicable. For over 2 centuries, Newton's law reigned unchallenged. It predicted eclipses, explained tides, mapped the motions of planets with astonishing precision. Astronomers like Edmund Halley used it to foresee the return of comets. Navigators trusted it to guide ships across the oceans. Engineers relied on it to construct the machinery of the Industrial Revolution. Gravity had become the very heartbeat of order, but there were whispers of anomalies. The orbit of Mercury, though nearly perfect, betrayed a small discrepancy. Its ellipse precessed more than Newton's law could account for. The differences were minute, but undeniable. Something subtle, something profound, was missing from Newton's universe. Then came Albert Einstein. In 1915, Einstein tore away the last veil. In his general theory of relativity, he transformed gravity from force into geometry. Space and time, once a backdrop for events, became players in the drama themselves. Mass, he declared, tells spacetime how to curve. Curved spacetime tells mass how to move. What Newton called an invisible force was, in Einstein's vision, the very shape of reality. Planets do not orbit because an invisible tether pulls them. They orbit because spacetime itself is curved into paths that bend. The Earth falls freely around the Sun, not tethered by force, but gliding along a geodesic, the straightest possible line in a curved cosmos. The apple falls because the Earth, beneath it, curves spacetime inward. Objects move, not toward Earth, but through spacetime itself, which funnels them down. In this revelation, gravity ceased to be a mysterious action at a distance. It became the architecture of existence, and like Newton's before him, Einstein's equations made predictions. If gravity is curvature, then light itself, though massless, must follow the curves. In 1919, Arthur Eddington journeyed to Principe Island to observe a solar eclipse. As the sun's light was blotted out by the moon, stars near the solar limb came into view. Their positions, shifted by the sun's mass-bending spacetime, confirmed Einstein's theory. The universe was curved, and gravity was not force, but geometry. The impact was seismic. Newspapers declared that Newton's laws had been overturned, that the universe itself was rewritten. In truth, Newton's law remained an extraordinary approximation, still useful, still powerful. But Einstein had shown its deeper truth. Gravity was not simply a pull, but the shape of time itself. From then onward, astronomers and physicists saw the cosmos through a new lens. They measured the precession of Mercury with perfect accuracy. They observed the bending of starlight. They calculated gravitational time dilation, the slowing of clocks in stronger fields. The theory that began as an abstract set of equations soon became essential in practical life without relativistic corrections. GPS satellites would drift miles off course each day. Gravity was no longer simply the invisible tether that Newton described. It was the sculptor of reality. It was the reason light bent, time slowed, and orbits shifted. And yet, with Einstein's revelation, the mystery only deepened. For if gravity is the shape of spacetime, then what is spacetime itself? What fabric is it woven from? What lies beneath? The curves, from Aristotle's falling stones to Galileo's experiments, from Newton's universal law to Einstein's curved spacetime, gravity had revealed itself, layer by layer, familiar yet ever evasive, simple yet infinitely profound. Each discovery brought humanity closer, and yet always left a question unresolved. The realization stood clear. Gravity was not only the force that binds planets, stars, and galaxies. It was the weaver of the cosmos, the hand that shapes existence. Itself, and still, behind its grip, its weight, its inevitability, one haunting question endured, not how gravity works, but why it exists at all. The story had only begun. The early 20th century had placed gravity upon a throne of elegance. Einstein's equations did not merely predict the orbits of planets. They foretold new realities, black holes, expanding universes, the slowing of time itself. Yet with every triumph, gravity also unveiled contradictions so vast they shook the foundations of physics. The first shock lay in gravity's dual nature, the weakest of the forces, yet the ruler of the cosmos. Between two protons, the electromagnetic repulsion is 10 times stronger than their gravitational pull. Gravity is so feeble that a small magnet can lift a paperclip against the pull of the entire Earth. And yet, this feeble force commands galaxies, dictates the lives of stars, sculpts the universe on its largest scales. It seemed paradoxical, a force too weak to matter in the laboratory, but too powerful to ignore in the cosmos. The second shock was the singularity. When Karl Schwarzschild, serving in the trenches of the First World War, solved Einstein's field equations, he uncovered something extraordinary. His mathematics described a region where escape became impossible, where space-time folded inward upon itself, a black hole. At its heart, the equations pointed to a singularity, a point of infinite density, where space and time themselves ceased to have meaning. Einstein himself resisted the idea. The notion that nature would permit infinities offended physical intuition. For decades, black holes were treated not as real objects, but as oddities of mathematics. Yet the equations did not waver, and when evidence mounted, the collapse of massive stars, the energy of quasars, it became clear singularities were not fantasy, they were destiny. Infinity had crept into the laws of physics, and gravity had revealed a place where science itself might break. Then came the event horizon. Unlike any boundary known before, it was not a surface of matter, but of information. Cross it, and return became impossible. Beyond it, not even light, the swiftest traveler in existence, could escape. The event horizon was the ultimate manifestation of gravity's refusal to let go. To the outside universe, anything falling in was lost forever. For the first time, physics confronted a prison with no key, a silence no signal could break. But the shocks did not end at black holes. On the grandest scales, astronomers believed gravity's steady hand would slow the expansion of the universe, perhaps one day reversing it. Yet, in the late 20th century, measurements of distant supernova unveiled an opposite truth. The universe was not slowing, it was accelerating. Some unknown force, dubbed dark energy, was pushing space-time apart faster and faster. Gravity, the eternal gatherer, was losing to something unseen. The cosmos would not collapse back into fire, it would expand into cold. Here lay a new shock. Gravity was not absolute ruler, but competitor. Its grip challenged by a mysterious rival, and still deeper contradictions emerged at the smaller scales. For the other three forces of nature, electromagnetism, the strong nuclear force, the weak nuclear force, physics had forged a quantum description. Each force could be understood as the exchange of particles within quantum fields, photons. For electromagnetism, gluons for the strong force, W and Z bosons for the weak. Gravity, by all expectation, should also yield a quantum messenger, the graviton, a particle of pure geometry, but attempts to quantize gravity led only to infinities, two equations that dissolved into meaninglessness. The universe had split into two languages. On one side, Einstein's general relativity, smooth and continuous, describing planets, stars, and galaxies with perfection. On the other, quantum mechanics, discrete and probabilistic, explaining the subatomic world with astonishing accuracy. Both worked, both triumphed, but together they refused to agree. At the very places where both must matter, at singularities, at the birth of the universe, the equations broke down. Here lay the greatest shock of all. Gravity resisted unification. Every other force found its place in quantum fields. Gravity alone stood apart, irreducible, untamed. It clung to space-time itself, unwilling to bend to the rules that governed every other corner of nature. The consequences were staggering. If nothing escapes a black hole, what happens to the information carried by matter that falls in? Does it vanish? Quantum theory insists that information is never destroyed. Gravity insisted otherwise. This was not a small discrepancy, was a paradox. If information truly disappears inside black holes, then quantum theory collapses. If it does not disappear, then gravity, as Einstein described it, cannot be complete. In either case, the pillars of physics trembled. Stephen Hawking confronted this paradox in the 1970s, when he discovered that black holes are not truly black. Through quantum effects at the horizon, they radiate energy, slowly evaporating over eons. But if they vanish, what of the information they swallowed? Is it erased forever, or somehow encoded in their radiation? No answer satisfied both relativity and quantum mechanics. The information paradox became a wound at the heart of physics. Still unhealed, the shocks multiplied. Time itself bent under gravity's weight. Experiments confirmed that clocks run slower near stronger gravitational fields. A person living near a mountain peak ages slightly faster than one at sea level. Astronauts orbiting Earth live a little longer than those bound to its surface. Gravity had revealed itself not only as the shaper of space, but as the sculptor of time. Past, present, and future flowed differently depending on where one stood. The universality of time, once thought absolute, dissolved into relativity. In laboratories, physicists found gravity impossible to ignore even in the mundane. Global positioning system satellites must account for relativistic time dilation, both from their speed and their distance from Earth's mass. Without Einstein's equations, GPS devices would drift kilometers off course each day. What began as a cosmic theory became an everyday necessity, and yet the paradox persisted. Gravity was both everywhere and nowhere. It ruled the universe, but remained the most mysterious of forces. Its shocks were not confined to mathematics. They reshaped how humanity understood reality itself. Consider the duality. Gravity is weakness and strength, freedom and prison, order and chaos. It collapses stars into singularities, but also allows galaxies to coalesce. It sculpts beauty and devours it. It binds the cosmos together, but may conceal its deepest truths. It is, at once, the most familiar experience, the weight beneath our feet, and the most alien, tearing the fabric of reality into paradox. The scientific community stood in awe, both triumphant and humbled. The laws that guided spacecraft across the solar system, the laws that bent starlight around the sun, were also the laws that dissolved into infinities inside black holes. Humanity had discovered not just a force, but a frontier of ignorance. The scientific shock of gravity was not simply that it governed so much, it was that it revealed how little could be understood without it. Every attempt to reconcile it with quantum mechanics ended in failure. Every glimpse into its extremes, the first moments of the Big Bang, the centers of black holes, ended in paradox. Gravity, it seemed, was both the oldest truth and the newest mystery. It was the keeper of time, the sculptor of space, the destroyer of certainty. It was the hand that built the universe, and the silence that refused to explain why. And as scientists looked deeper, they realized the shocks were not diminishing. They were multiplying. Each discovery led not to closure, but to escalation. For every triumph of understanding, gravity seemed to whisper another riddle. The universe, bound by its grip, was not yet ready to yield its secret. The shocks of gravity had shaken physics. Yet instead of retreating, humanity pressed further. If gravity could not be tamed by equations alone, then perhaps it could be illuminated by observation, by listening to the universe where its grip was strongest, and watching where its hand shaped the cosmos. The laboratories of gravity were vast and varied. Some stretched across the heavens, others hidden in mountains and deserts. Each instrument was not merely a tool, but a lens into the unseen. Together they formed a chorus of listening, probing, and waiting for gravity to speak. Black holes became the first stage for this deeper investigation. Once dismissed as mathematical curiosities, they emerged as real, luminous laboratories of extreme gravity. When a star many times the mass of the sun exhausted its fuel, its core collapsed, and spacetime itself caved inward. Matter spiraled toward the event horizon in furious whirlpools, heated to millions of degrees, radiating X-rays that pierced the void. Satellites in Earth's orbit, Chandra, XM Newton, New STR, traced these signals, revealing systems where invisible black holes consumed their companions, siphoning matter in a gravitational dance of doom. These X-ray binaries became nature's declarations. Black holes were not fantasy. They were here, and they were hungry. Quasars deepened the revelation. In the 1960s, astronomers studying faint points of radio light found objects more distant, more luminous than any star. These quasars blazed with the energy of 1 trillion suns, yet from a region no larger than the solar system. Their power could only come from matter plunging into supermassive black holes. Suddenly, gravity was not merely a local sculptor, but a cosmic architect, driving the brightest beacons in the universe. It was in the act of devouring that gravity announced its existence most clearly. Then, in 2015, a new kind of observation shattered silence itself. Deep beneath the Earth, in tunnels 4 kilometers long, twin detectors in Louisiana and Washington lay in waiting. They were designed not to see light, but to feel tremors in the fabric of spacetime itself. And on September 14th, they did. 2 black holes, more than 1 billion light-years away, spiraled together and merged. Their collision sent ripples racing across the universe, stretching and compressing space like the surface of a pond struck by stones. When these ripples washed across Earth, the detectors registered the faintest echo, a whisper of gravity itself. This was LIGO's triumph, the first detection of gravitational waves. At last, gravity had been heard. It was not silent curvature, but a music woven into spacetime. Einstein's century-old prediction had become sensation, and with it, the cosmos opened a new sense gravitational wave astronomy. The universe could now be seen not only in light, but in sound, a deeper language of its violence and birth. Further investigations pressed into the subtlety of gravity's distortions. Pulsars, rapidly spinning neutron stars, remnants of collapsed suns became precision clocks scattered across the galaxy. Their beams of radio light swept Earth in intervals so regular they rivaled atomic clocks. When gravity from orbiting companions or cosmic structures bent their pulses, the delays revealed secrets with exquisite precision. The precession of binary pulsars confirmed Einstein's equations to astonishing accuracy. And yet, hidden in these confirmations was also the weight of unanswered questions. Why did relativity work so well, even where it should fail? Closer to home, satellites carried clocks that ticked differently depending on their orbits. Global positioning systems became unintentional laboratories of relativity. Engineers were forced to account for both special relativity, the satellite's motion, and general relativity, the weaker pull of gravity at altitude. Without these corrections, location data would drift miles each day. Gravity, far from abstract, dictated the rhythms of everyday technology. But it was in the quantum realm where deeper investigation faltered. Attempts to unite gravity with quantum theory produced only equations that unraveled. Efforts to describe gravity as particles' hypothetical gravitons led to infinities no mathematics could renormalize. In contrast, electromagnetism and nuclear forces yielded easily to the quantum framework. Gravity resisted as though it was something fundamentally different, or perhaps not fundamental at all. Dark matter expanded the enigma. In the 1970s, astronomer Vera Rubin measured the rotation of galaxies and found that stars orbited too quickly. By Newton and Einstein's laws, they should have flown apart. Yet galaxies held together. Something unseen was binding them, an invisible mass exerting gravitational pull. This dark matter, 5 times more abundant than ordinary matter, had never been detected directly. Its existence was inferred only by gravity's stubborn fingerprints. Gravity seemed to point toward something hidden, an unseen architecture of the cosmos. Dark energy compounded the puzzle. Where gravity should have slowed the universe's expansion, observations revealed acceleration. The cosmos was not only expanding, It was expanding faster with time. Gravity was not enough to explain it. Some opposing force, some energy in the fabric of space itself, was driving galaxies apart. Investigations of supernova, cosmic microwave, background maps, and galaxy surveys all converged on the same truth. Gravity was not supreme, but challenged by a deeper mystery. Simultaneously, supercomputers recreated universes in silico, modeling how gravity guided matter into filaments and voids, forming the cosmic web. These simulations mirrored reality with eerie accuracy, yet required dark matter and dark energy to succeed. Gravity itself seemed consistent only if partnered with two unseen entities. It was as if nature insisted. Gravity alone was never the full story. The deeper investigation did not diminish gravity's contradictions. Instead, it expanded them. Every new instrument confirmed Einstein's predictions, yet every cosmic frontier revealed phenomena his equations could not explain. Black holes, gravitational waves, dark matter, dark energy, each a testament to gravity's grip, and each a doorway to ignorance. In laboratories beneath mountains, physicists built detectors filled with liquid xenon and germanium, waiting for particles of dark matter to collide. None came. At particle accelerators, protons were smashed to probe extra dimensions where gravity might leak. None were found. Telescopes scanned quasars, pulsars, colliding galaxies, looking for cracks in Einstein's theory. None appeared. Gravity remained unbroken, even as it defied explanation. The investigation deepened into paradox. Gravity explained everything, yet it explained nothing fully. It governed planets, but not particles. It predicted galaxies, but not their hidden matter. It bent light, but not quantum fields. It resisted unification, refused quantization, and yet ruled the universe as if no rival could exist. Here the enigma sharpened. Perhaps gravity was not fundamental at all. Perhaps it was emergent, a byproduct of deeper laws, like temperature, emerging from the jostling of atoms. The investigations did not resolve the mystery. They only widened it, and still the scientists listened to the silent merging of black holes, to the whisper of pulsars across the galaxy, to the faint lensing of starlight bent by dark matter. Every observation was both triumph and torment, triumph in what it confirmed, torment in what it concealed. The deeper the investigation went, the clearer it became. Gravity was not only a force of attraction, but a force of paradox. It gave answers only to lead toward further riddles. The universe was bound together by something it did not yet understand, and in that mystery lay both awe and unease. Gravity's mysteries did not recede under the glare of observation. They multiplied, refracting into paradoxes that pulled theory in opposing directions. Each triumph seemed to open a deeper well. The closer science approached gravity's core, the more it felt the tug of questions that would not release their hold. The black hole, once a reluctant theoretical possibility, became the stage where gravity's insistence turned to obsession. At the brink of its event horizon, two visions of the universe collided. General relativity promised a smooth crossing for any brave particle or photon. Nothing special at the horizon, only the gentle relentlessness of free fall. Quantum theory murmured a warning. Information cannot be lost. The two claims could not both be true in their naive form. Out of this contradiction rose the information paradox, a wound at the seam of physics. If a black hole swallows matter and later evaporates, does the information contained within that matter vanish? Quantum mechanics forbids such erasure. Relativity seems to permit it. Gravity tightened its grip not only on matter, but on the very logic of physical law. The wound deepened with the firewall paradox. In seeking a reconciliation, some theorists proposed that the event horizon might be ringed by a searing wall of high-energy quanta, a furnace that incinerates anything attempting to cross. This firewall would preserve information by violently disrupting the smooth spacetime that relativity guarantees. If it exists, the horizon is no longer a quiet threshold, but a rupture in the gentleness of freefall. If it does not, information must escape the black hole in ways that defy simple storytelling. Either way, the harmony between gravity and quantum theory fractures at the very place where gravity claims absolute dominion, beyond individual black holes. Gravity's urgency echoed across cosmic scales. Astronomers found supermassive black holes in galaxies so young that their existence seemed to outrun time. Quasars blazing less than 1 billion years after the Big Bang required central engines, millions or billions of times the Sun's mass. The usual recipe, small stellar black holes, slowly fattening on gas, proved too slow. Gravity appeared to be working faster than models allowed, assembling giants in a cosmic instant. Speculative scaffolds arose, direct collapse black holes forming from pristine clouds, runaway growth fed by dense streams of gas, mergers of black hole seeds in crowded protogalactic wombs. Each scenario stretched plausibility, yet observations demanded haste. Gravity did not merely hold, it accelerated. The cosmic web emerged as gravity's grand design, filaments of dark matter threading the universe, galaxies glistening like dew along their strands, voids yawning in between. Supercomputer simulations, seeded with tiny quantum fluctuations from the infant universe, produced webs that matched observations with haunting fidelity. Yet success sharpened the question, why this pattern? Why does gravity, left to run its course, weave a tapestry of filaments and nodes, a fractal-like architecture spanning hundreds of millions of light-years? The answers seemed to fold back to initial conditions, to inflation's quantum seeds. But gravity's role as loom and weaver remained more poetic than fully derivable. It made the universe look inevitable. And yet the parameters of that inevitability still felt borrowed from elsewhere. Meanwhile, the accelerating expansion of the universe refused to abate. Dark energy, the name given to the unknown driver, acted like a repulsive pressure, suffusing space itself. On scales of stars and galaxies, gravity wins, pulling and binding. On scales of millions of light-years and beyond, dark energy takes command, pushing and thinning. The universe, it seemed, was governed by a delicate stalemate, a treaty between attraction and repulsion. Gravity, in this treaty, was both indispensable and insufficient, powerful enough to craft galaxies, powerless to halt the widening of everything. The spectre of a big chill, a future where stars exhaust their fuel. Galaxies drift beyond one another's horizons, and the sky goes dark, grew harder to ignore. Gravity cannot let go locally, but the cosmos may yet slip away globally, at smaller scales. Gravity's reach became strangely contingent. Galaxies spun too fast for their visible matter. Clusters bent light more strongly than their luminous mass allowed. The standard answer, dark matter, retained its throne, invisible but gravitationally manifest, and yet alternative whispers lingered. Perhaps gravity itself changes behavior at low accelerations. Perhaps Newton's inverse square law is not universal in the deep outskirts of galaxies. These modified gravity ideas explained some rotation curves, but stumbled against the full suite of data. Still, their persistence illustrated gravity's refusal to be simple. Either unseen matter dominates, or gravity wears different masks in different regimes. In both readings, ignorance remains gravitationally bound. The quantum frontier proved no gentler. Attempts to quantize gravity, to describe spacetime with the grammar that governs electrons and quarks, confronted infinities that resisted the usual renormalization cures. String theory offered a sweeping vision, gravity as the vibration of closed strings, spacetime geometry arising from a deeper, extended structure. Loop quantum gravity proposed a granular spacetime woven of discrete loops that avert singularities and replace the Big Bang with a big bounce. The holographic principle, born from black hole thermodynamics, suggested that a region's physics might be encoded on its boundary, as though the volume is a projection from a lower dimensional screen. Each path opened vistas, solved partial problems, and then met new cliffs. The unification crisis did not dissolve, it diversified. Gravity seemed to lead everywhere, and to one place at once, a summit hidden by clouds, even successes raised. Unsettling corollaries. The Bekenstein-Hawking formula tied a black hole's entropy to the area of its horizon, not its volume, a relation that whispered of holography and of information bound to surfaces. The area law fit beautifully with quantum field theory in curved spacetime, and yet invited a deeper question. If entropy and information live on boundaries, is spacetime itself emergent, stitched together from entanglement patterns, the way temperature emerges from molecules? In this tale, gravity is not fundamental, it is entropic, a statistical draw toward configurations that maximize information. The pull that shapes galaxies would, in this picture, be the universe remembering how to arrange itself. It is a radical kindness and a radical demotion to gravity, recasting it as the echo of hidden microstat. At the threshold of measurement, gravity wove paradox into practice. Ultra-precise atomic clocks, separated by centimeters in height, ticked at measurably different rates, testifying to time's sensitivity to gravitational potential. Bose-Einstein condensates and optomechanical resonators began to probe whether gravity can entangle masses, a subtle doorway to seeing whether gravity itself must be quantum. If tiny objects can share quantum correlations mediated solely by their mutual attraction, then gravity would reveal a quantum face. If not, perhaps it stands outside the quantum family. Experiments pressed forward, inch by inch, as if climbing a mountain with instruments made of snowflakes. Observatories multiplied gravity's voices. The Event Horizon Telescope sketched the glowing silhouette of black hole shadows, rings of light imprisoned in orbit by spacetime's curvature. LIGO, Virgo and Cagra amplified the universe's tremors, hearing not only black holes but neutron stars collapse and collide. Soon, Lisa will unfurl in space to listen for the baritone of supermassive mergers, and pulsar timing arrays will survey the cosmic low hum of gravitational waves from countless distant binaries. Each detection is a confirmation and a question. Wrapped in confirmation, the waveforms fit relativity with uncanny precision. The sources sometimes arrive too early, too massive, too eager. Gravity proves itself right by confronting new wrongs. Philosophically, escalation turned to vertigo. If gravity is geometry, then the universe is a map that draws itself. If gravity is information, then the universe is a story that remembers how it is told. If gravity is emergent, then the universe is a phase of matter whose deeper constituents we have not yet seen. In every lens, gravity remains the shape of necessity, a law that compels motion and also compels the mind to reinterpret. Law itself, emotionally, escalation invited awe, edged with dread. Gravity is cradle and more, the force that gathers stars, and the force that hides the truth of what it gathers. It composes galaxies into symphonies, then lowers the baton into silence at the edge of the horizon. It slows clocks into differing truths, forces rulers to disagree on lengths, decides who ages faster and who sees the universe blink more slowly. It is a politics of reality to which everything submits. And still, the questions circle. Does information truly survive the death of a black hole, sewn into outgoing radiation in patterns too subtle for current theory? Does dark matter exist as a new family of particles, or is gravity itself different in the realm of faint accelerations? Is dark energy a constant pressure in space-time, or a sign that gravity's equations mutate on the largest canvases? Do wormholes stitch distances together and encode entanglement, or are they fables of mathematics that reality refuses to perform? Escalation does not announce a crisis, it accumulates one. Gravity will not let go of the universe, and the universe will not let go of gravity's secrets. Each paradox is an orbit, each solution a perihelion that precesses into another question. The path forward is curved, like the geodesics it describes. The deeper science falls into gravity's well, the more it realizes that falling is not descent alone. It is also approach toward a horizon that forever recedes, promising that beyond every proof lies another pull. When observation reaches its limits and equations begin to tremble under paradox, speculation rises, not as fantasy, but as the scaffolding upon which new science is built. Gravity, the oldest companion of physics, stands at the heart of these speculations, refusing to reveal its final identity. Theories multiply, each proposing a different mask for the force that binds all motion, and each beckoning toward truths that may yet remain hidden beyond reach. One of the most ambitious frameworks is string theory. Here, gravity is not a fundamental force in the traditional sense, but the vibration of tiny, one-dimensional strings of energy. In this vision, every particle, electron, photon, quark is a note played on these strings, their identities determined by frequency and mode. Gravity arises from the closed loops, vibrations that circle upon themselves, their excitations interpreted as hypothetical particles called gravitons. If true, spacetime is not continuous but resonant, a symphony of quantum chords in higher dimensions. String theory whispers of 10, even 11 dimensions, curled so tightly that they evade direct perception. Gravity's weakness, under this account, is not a defect but a signature of its diffusion into those unseen dimensions. Though unproven, the mathematics of string theory has produced fertile insights, knitting together black hole entropy and holography, suggesting that gravity is less a solitary ruler and more a consequence of deeper, multidimensional harmonies. A rival vision takes a more minimalist path. Loop quantum gravity, LQG, where string theory extends spacetime into higher dimensions. LQG attempts to quantize spacetime itself. It proposes that geometry comes in discrete quanta, woven from tiny loops of gravitational fields. Volumes, areas, and distances are no longer infinitely divisible but pixelated, built from indivisible units. In this granular fabric, singularities vanish. The infinite densities of black holes and the Big Bang are replaced by finite transitions. Instead of a beginning, a big bounce emerges, a prior universe collapsing into the seed of the next. Gravity here is not emergent, nor dependent on higher dimensions. It is fundamental, the skeleton of space itself. Yet LQG struggles to unify with the other forces and particles, to weave electromagnetism and nuclear forces into its network. Still, its promise lies in offering a vision where the very act of measurement, length, time, area, dissolves into the discreteness of geometry. Hovering between these visions is the holographic principle, a revelation sparked by a black hole. Thermodynamics. If a black hole's entropy is proportional not to its volume but to the surface area of its horizon, then perhaps the same rule applies universally. The physics within a region of space can be described by information encoded on its boundary. Reality, in this telling, is a projection, like a three-dimensional image cast from a two-dimensional film. Gravity, in turn, would not be a fundamental force, but an emergent property of this encoding. The curvature of space arising from the flow of information across boundaries. The ADS-CFT correspondence, one of string theory's crown jewels, provided a concrete mathematical case, a gravity-filled universe in bulk. Space could be equivalent to a quantum field theory on its surface. If true, the universe is less like a stage of objects moving through space, and more like a story written on the walls of a cosmic cave, shadows playing into dimensional depth. Gravity, then, would be the illusion of solidity produced by informations. Geometry. This idea resonates with the radical concept of entropic gravity proposed by Eric Verland. Here, gravity is not a force at all, but an emergent tendency, like temperature or pressure. Just as heat emerges from the collective jostling of molecules, gravity emerges from the statistical behavior of hidden microstates of spacetime. Matter, moving toward matter is, in this view, the unfolding of entropy, the system's drive to maximize informational balance. Planets orbit stars, not because of invisible strings or warped space, but because the entropy of the universe increases when they do so. This picture reframes gravity, not as an active agent, but as a memory, the cosmos, remembering its preferred arrangements. While controversial and incomplete, entropic gravity offers testable deviations at galactic scales and has sparked attempts to explain phenomena like dark matter without new particles. As entropy itself accounts for missing gravitational pull, other theories suggest that gravity's refusal to let go may be because it is not confined to our universe at all. Brain-world cosmologies, born from string theory, propose that our cosmos is a three-dimensional membrane floating in a high space. Gravity, unlike electromagnetism and nuclear forces, seeps into these extra dimensions, weakening its hold in ours. Its apparent fragility, then, is the consequence of its diffusion beyond the stage we see. Some models suggest collisions between brains could ignite new Big Bangs, cycles of creation born of higher dimensional tremors. In these tales, gravity is not only the shaper of our universe but the bridge between universes, the one force that dares to cross boundaries. Others have tried to modify gravity directly. Modified Newtonian dynamics, Mond and its successors, propose that Newton's laws, and even Einstein's, are not fully correct at the faint accelerations seen in galaxies. In this telling, stars orbit faster, not because of invisible dark matter, but because gravity itself behaves differently in low acceleration regimes. while Mont explains galactic rotation curves with elegant precision. It falters at the scales of galaxy clusters and the cosmic microwave background, yet it endures. A reminder that what is called dark matter may be less an unseen substance and more an unseen law. If Mond or similar modifications prove true, the greatest mystery of modern cosmology, the missing mass of the universe, would not be an absence, but a misinterpretation. At the farthest reaches of speculation lies the possibility that gravity is not fundamental at all. Perhaps it is emergent, not from entropy or holography alone, but from the fabric of quantum entanglement. Some researchers propose that spacetime itself is knitted together by patterns of quantum entanglement, that the connectivity of space arises from the correlations of quantum states. If entanglement is broken, space unravels. If entanglement flourishes, geometry emerges. In this account, gravity is the manifestation of entanglement's architecture, the macroscopic echo of microscopic bonds. Wormholes, once dismissed as curiosities, find new relevance here. Some conjecture that they are the geometric expressions of entangled pairs. E equals EPR, connecting Einstein-Rosen bridges to quantum entanglement. Gravity, in this light, is not a sculptor but a song, a resonance produced by the universe's insistence on being connected. Speculations stretch even further into cosmology. Some suggest that black holes may not be endpoints but gateways, their interiors giving birth to new universes. In such scenarios, every singularity is not a collapse into nothing but a tunnel into another expansion. Each new cosmos budding like a fruit from the tree of space-time. Gravity, in this poetic yet serious speculation, is the midwife of multiverses. Its refusal to let go ensuring that no matter collapses without producing new horizons elsewhere. Others, like Penrose with his conformal cyclic cosmology, propose that the universe itself is cyclical, each eon ending in infinite expansion that becomes indistinguishable from the next Big Bang. Gravity's grip extends across eons, guiding the rhythm of universes themselves, ensuring continuity even as particulars dissolve. Philosophically, these speculations turn gravity into a mirror of existence itself. If it is fundamental, then it is the bedrock upon which all else is written, the oldest law, the one that will outlast every particle and field. If it is emergent, then it is memory, the echo of deeper principles that remain unseen, like the visible ripples on an ocean concealing the currents beneath. If it is entanglement, then it is intimacy, the universe compelled to remain connected, no particle allowed to drift into absolute solitude in every theory. Gravity remains the paradox it has always been, the gentlest force, the most dominant, the most familiar, the least understood. Each speculation is a spiral around a core that resists capture, a horizon that recedes as science approaches. Gravity cannot let go of matter, of light, of questions, and neither can the human mind let go of the effort to understand it. The quest to understand gravity has never been a matter of equations alone. It is also a matter of instruments, lenses and detectors, satellites and colliders, each one a hand extended into the cosmos, each one straining to touch the invisible hand that binds all motion. Gravity is not just a mystery. It is an adversary of silence, a presence that reveals itself only through subtle distortions, delicate ripples, faint curvatures of light and time. To capture it, humanity has had to build machines capable of hearing vibrations in space-time itself, of seeing shadows cast not by matter but by absence, and of measuring time with the precision of atoms. These tools have become the gateways through which the modern age approaches gravity's secret. Perhaps the most striking achievement is the Event Horizon Telescope (EHT), a planet-sized array of radio dishes spread across the Earth. In 2019, it delivered the first direct image of a black hole's shadow, a dark silhouette framed by luminous plasma spiraling into oblivion. That image, the heart of galaxy M87, was not a photograph in the conventional sense, but a reconstruction from interferometry, combining signals across continents to achieve resolution finer than any single telescope could dream of. In the fiery ring surrounding the shadow lay confirmation of Einstein's equations, gravity bending light exactly as predicted. Yet behind the triumph lurked the deeper question: is the shadow truly a product of general relativity alone, or does it hide signatures of new physics at the edge of spacetime? Future upgrades to the EHT aim to capture not just still images, but movies of black holes, watching matter fall and light swirl in real time. In the flickering glow, physicists hope to detect deviations, the faint fingerprints of quantum corrections, or exotic geometries. Equally revolutionary has been the rise of gravitational wave astronomy. In September 2015, the Laser Interferometer Gravitational Wave Observatory LIGO recorded the merger of two black holes, their collision releasing more energy in a fraction of a second than all the stars in the observable universe combined. But this energy did not radiate as light. It rippled through spacetime, stretching and squeezing the very fabric of reality. LIGO's twin detectors in Louisiana and Washington sensed these distortions as changes smaller than the width of a proton, the result of laser beams traveling down 4-kilometer vacuum arms. Since that first detection, dozens of gravitational wave events have been observed, including the spectacular merger of neutron stars in 2017, which lit the sky with kilonova light and seeded the cosmos with gold and platinum. Gravitational waves provide a new language for gravity, not images, not spectra, but vibrations that carry stories of invisible collisions across billions of years. As detectors like Virgo in Italy and Kagra in Japan join the network, and as upgrades expand sensitivity, a new era unfolds, an era in which the universe can be heard, not just seen. The next great step will be taken into space itself. The Laser Interferometer Space Antenna LISA, planned for the 2030s, will place 3 spacecraft millions of kilometers apart in a triangular formation, their lasers measuring space-time distortions across cosmic distances. Where LIGO listens to stellar mergers, LISA will hear the thunder of supermassive black holes colliding, events that reshape entire galaxies. It may even detect whispers from the early universe, gravitational waves imprinted moments after the Big Bang. With LISA, physicists will test general relativity in the strongest possible fields, searching for deviations that might point to quantum gravity. Each ripple will be a probe into domains where no other signal can reach. While gravity is measured in collisions and shadows, it is also tested in the mundane, in satellites orbiting Earth and clocks ticking in laboratories. The Global Positioning System, GPS, built for navigation, must account for both special and general relativity. Clocks on satellites run faster than those on Earth, lifted slightly away from gravity's grip. Without relativistic corrections, GPS would fail within hours. These systems transform everyday life into a constant experiment. Each successful measurement of location a silent confirmation that Einstein's theory still holds. But researchers push further. Atomic clocks now, measure time so precisely that they can detect gravitational redshifts across a single centimeter of elevation. With these instruments, physicists map Earth's gravity in exquisite detail, but also test the universality of time dilation, probing whether the fabric of reality hides imperceptible cracks. At cosmic scales, the search takes form in surveys of dark matter and dark energy, both phenomena intimately tied to gravity. The Veracruz-Rubin Observatory in Chile will soon begin mapping billions of galaxies, tracing their positions and shapes over cosmic time by measuring gravitational lensing, the bending of light by invisible mass. It will construct a cartography of dark matter, mapping the unseen scaffolding of the universe. Meanwhile, the Euclid mission, launched by the European Space Agency, scans the geometry of cosmic expansion, measuring how galaxies cluster and how dark energy accelerates the cosmos. These surveys test not only the presence of dark matter and energy, but whether gravity itself behaves differently across scales. If general relativity fails in the cosmic arena, its betrayal will be written in the curves of galaxies and the warping of light. On the frontiers of energy, physicists turn to particle colliders, such as the Large Hadron Collider (LHC). While colliders are often seen as instruments for particle physics, they are also laboratories for gravity at the smallest scales. Some theories predict that gravity may reveal itself through extra dimensions, producing microscopic black holes or missing energy signatures. Though no such events have yet been found, the search continues. Each collision a test of whether gravity is confined to spacetime or leaks into hidden realms. Future colliders, more powerful than the LHC, aim to push further, probing whether quantum gravity phenomena can ever be seen in accelerators at the level of simulation. Supercomputers act as laboratories of the mind, solving Einstein's equations in regimes too complex for pen and paper. They recreate mergers of black holes, the collapse of stars, and the growth of galaxies across billions of years. Each simulation is compared with gravitational waves, with telescope data, with cosmic surveys. The convergence of theory, observation, and computation turns gravity into a triangulated mystery, tested from the small to the vast, from the violent to the subtle. Radio telescopes to contribute to gravity's interrogation by observing pulsars, neutron stars that rotate with clockwork. Precision astronomers test Einstein's theory in extreme conditions. Binary pulsars, pairs of neutron stars orbiting one another, lose energy precisely as predicted by gravitational radiation, long before direct detection was achieved. Today, pulsar timing arrays stretch across continents, listening for low-frequency gravitational waves from supermassive black hole binaries. Each tick of a pulsar is a cosmic metronome, its irregularities revealing the tremors of gravity across intergalactic distances. And still, beyond instruments already built, science dreams of those yet to come. Next-generation X-ray observatories, such as Athena, will peer into accretion disks around black holes, mapping how matter falls under gravity's extreme grip. Future optical giants, like the extremely large telescope ELT in Chile, will observe stars orbiting the black hole at the center of the Milky Way, testing relativity with each flicker of light. Projects like LOVOIR and the Origins Space Telescope imagine still deeper gazes, hoping to see the fingerprints of gravity not only in galaxies but in the faint whisper of the first stars. The relentless effort stretches across disciplines: astrophysicists observing galaxies, particle physicists colliding protons, geophysicists measuring time shifts in laboratories, Each is united by a single aim, to force gravity to reveal whether it is fundamental or emergent, whether it is geometry or memory, whether it is the final truth or merely the shadow of deeper laws. And yet, the irony persists. The more tools humanity builds, the more gravity confirms Einstein, repeating predictions with stubborn perfection. No deviation has yet broken the symmetry. The hope of quantum gravity remains suspended, the instruments catching only the elegance of relativity. Still, science presses forward, knowing that one day, perhaps, a ripple to faint or a shadow to sharp will betray the secret, for gravity will not let go of the universe, nor will the universe let go of the pursuit to understand gravity. Every telescope, every detector, every clock is a reminder. The search is not only for equations, but for meaning. To build these tools is to admit that the mystery is larger than any one experiment, larger even than any one age. The search is perpetual, an echo of gravity itself, persistent, unyielding, forever binding science to its enigma. Gravity has always been described as a law, a force, an equation. But beyond numbers, beyond geometry, it is something older, something more intimate. It is the whisper of the universe telling matter where to move, the invisible thread weaving every star and every life into a single fabric. In the silence of night, one does not see gravity, one feels it in the orbits of the moon, in the fall of rain, in the weight of one's own body pressed to earth. To the physicist, it is curvature of spacetime. To the poet, it is the hand that holds everything together. And yet, gravity never truly reveals itself. For all the triumphs of Newton and Einstein, for all the instruments straining to measure its every nuance, the heart of gravity remains concealed. Unlike electromagnetism, it has no opposite, no repulsion to balance its embrace. Unlike the nuclear forces, it is not confined to atoms. It stretches across galaxies, across billions of light years, and yet cannot be reconciled with the smallest quantum. This contradiction is more than technical, it is existential, for gravity stands at the boundary between what humanity knows and what it longs to understand. There is a haunting fragility to this. Gravity is weak, so weak that a small magnet can lift a nail against the pull of an entire planet. And yet, it is also the architect of galaxies, the sculptor of cosmic webs, the keeper of black holes. Its paradoxical nature, frailty in the laboratory omnipotence in the cosmos, makes it a mirror of human existence. Fragile and powerful, temporary and eternal, insignificant and yet central. When scientists contemplate the far future of the universe, it is gravity that decides the script. If dark energy prevails, space will expand ever faster, scattering galaxies until only cold isolation remains. If gravity were stronger, the cosmos would collapse, returning all matter into a final singularity. Every star's life, every planet's orbit, every breath of existence, all balanced upon this one enigma that both permits creation and ensures destruction. The universe itself is a negotiation between gravity's hold and the expansion that seeks to escape it. Perhaps what unsettles most is not that gravity shapes the cosmos, but that it shapes time itself. Near a black hole, time dilates seconds, stretching into eternities. Even here on Earth, clocks on mountaintops run faster than those at sea level. Time, the most intimate measure of human experience, is not absolute but weighted by gravity. The implication is profound. Gravity does not simply govern where we are, but when we are. It ties existence not only in space, but in duration. It is, in a sense, the weight of time itself. In this way, gravity becomes more than a force. It becomes memory. Every orbit carries the remembrance of ancient motions. Every falling apple echoes the first stirrings of cosmic collapse. To be alive is to live within gravity's story, to inhabit its embrace without choice. And perhaps this is why philosophers often liken gravity to longing, to love, to bonds that never loosen. It is the connection that cannot be severed, the attraction that endures. But what if gravity is not fundamental at all? Some theories suggest it is emergent, born from deeper laws of information. If so, then everything humanity experiences, falling, orbiting, collapsing, may be shadows of hidden truths. Space-time itself may be woven from quantum entanglements, with gravity emerging like warmth from motion, or like pressure from countless particles unseen. This possibility shakes not only physics, but philosophy. If gravity is not fundamental, then what truly binds the universe? What deeper principle writes the script of reality? Such questions highlight a deeper truth. Gravity is not only an object of study, but a mirror of human limitation. Just as no one can step beyond the event horizon of a black hole, perhaps no one can step beyond the horizon of their own comprehension. To pursue gravity is to confront mystery itself, not as a temporary ignorance to be solved, but as an eternal frontier. The refusal of gravity to be unified with quantum mechanics is a reminder that knowledge is always partial, that reality forever exceeds the grasp of thought, and yet, in this humility lies wonder. For gravity's very silence makes its presence universal. Every child who leaps feels it. Every star that collapses announces it. Every galaxy that spins obeys it. The grandeur of gravity lies not only in its cosmic reach, but in its ordinary constancy. It is the reason the earth circles the sun, the reason oceans rise and fall, the reason human beings stand upon solid ground. It is both infinite and intimate. As science builds ever greater machines, telescopes stretching to the edges of time, detectors tuned to space-time's vibrations, the question remains, will gravity ever confess its final secret? Or will it remain like the shadow of a black hole, a shape defined by absence, a silence louder than any revelation? Perhaps the answer does not matter. Perhaps the pursuit itself, the centuries of falling apples, of bending starlight, of rippling waves is the meaning. For gravity teaches that the universe is held together not by certainty, but by connection. In the end, the gravity that cannot let go is more than a law of physics. It is a metaphor for existence itself. Lives are bound by invisible forces. Memory, love, time, just as stars are bound by the curvature of space-time. To live is to be held, to orbit within relationships, to fall and rise under forces never chosen. Gravity is both cage and sanctuary, both prison and foundation. It is the reminder that nothing is alone, that every mass feels every other, that all of existence is entangled in the same unyielding embrace. And so the final question lingers: is gravity the ultimate truth, the most fundamental of laws? Or is it merely the shadow of a deeper reality, a projection of something unseen? Whatever the answer, one truth remains. Without gravity, there would be no stars, no galaxies, no planets, no people. Without gravity, there would be no time, no story, no universe at all. The cosmos continues its dance. Galaxies circling, stars collapsing, black holes whispering at the edges of comprehension. And through it all, gravity holds, patient and silent, refusing release. It is the hand that cannot let go, the weight that binds reality to itself, the unseen fire in the heart of existence. As the universe expands into silence, as light grows faint and galaxies drift beyond sight, gravity endures. Perhaps not forever, perhaps not unchanged, but always as the principle that allowed something rather than nothing, structure rather than chaos, story rather than void. To contemplate gravity is to confront the essence of being, that to exist is to be bound, and to be bound is to be real. Thus the narrative closes where it began, with falling. The apple from the tree, the star into collapse, the galaxy into its orbit, all are falling endlessly, gracefully, inevitably. Gravity will not let go. And in its refusal lies not despair, but meaning. For in the invisible embrace of gravity, the universe finds coherence, and humanity finds its place, small, fragile, and yet part of the infinite weight of time.